We're diving straight into RIN VLA-002, a unified vision language action and world model, a really important paper coming out of Alibaba Demo Academy, Hupon Lab, and Zhejiang University.
And this paper, it really tackles one of the biggest bottlenecks in embodied AI right now.
Which is that fundamental separation between actually doing something and predicting what will happen.
Exactly. They've created this single unified framework that merges the policy part, that's the vision language action model, or VLA, with the foresight of a world model, the WM.
And the key insight really is that they actively help each other. The world model predicts what the future will look like, which helps the VLA plan better actions.
And it goes both ways. The VLA's understanding of what action to take and what it's seeing, that feeds back and actually makes the world model's predictions sharper. It gets better at imagining success.
Architecturally, they have two really clever solutions to make it all robust. First, there's an action-attention masking strategy.
Right, that stops errors from piling up when it's planning a sequence of actions.
And second, a hybrid design with a small, continuous action transformer head, which is just critical for making it work smoothly and quickly in the real world.
And the results really speak for themselves. RynnVLA-002 hit a 97.4% success rate on the LIBERO simulation benchmark. And what's crazy is it did this without any pre-training.
Which is a huge deal.
A huge deal. And in the real world, adding that world model boosted the success rate by 50%. It's just not an add-on, it's essential.
Okay, let's unpack this, because to really get the solution, you have to understand the problem they started with. Why do standard VLA models and world models, when they're separate, just hit a wall?
Right. So your standard VLA model is basically feed forward, it sees the world, gets an instruction, and spits out an action. That's it.
So the action is just an output. The model itself doesn't have an internal concept of what that action does to the world.
Precisely. It lacks, you could say, an imagination. It can't do counterfactual reasoning. It can't internally ask itself, okay, if I try to grab it like this, what happens next?
It's just matching patterns, not simulating physics. So when a grasp fails, it's lost.
It's totally lost. It just tries the next step in its memorized sequence because it doesn't understand why the world didn't react the way it expected. It has no explicit model of physics, of stability or contact.
Which is exactly the problem world models were supposed to solve, right? They're predictive. They forecast what the world will look like after an action.
Yes, they are the internal simulator, but they have their own major gap. They can't actually decide what to do.
They can't generate the action itself.
No. You need some other planner to feed it possible actions, and then the world model says, that's a good future, or that's a bad future. It adds a lot of complexity, a lot of latency.
So this is where RynnVLA-002 comes in as this really elegant solution, an autoregressive action world model.
It's dual purpose. It can be the VLA, the policy, or it can be the world model, the predictor. And it forces both of those jobs to use a single shared group of parameters.
So the planner and the doer have to learn from the same brain, basically.
Exactly. And their choice of foundation model here is interesting. They started with Chameleon, which is already known for being good at both understanding and generating images. A perfect base.
Let's talk about how they fuse everything together. The tokenization. You've got 4 different kinds of input: image, text, state, and action.
And every single token, no matter what it is, a pixel, a word, a joint angle, they all live in the same shared vocabulary. A big one, 65,536 tokens.
And that's so important because it means the transformer sees an image token and an action token as being in the same conceptual space. It allows for that really deep cross-modal understanding.
For sure. For the visuals, they use a VQGNN, which is pretty standard for getting good-looking images without being computationally insane.
But what about the robot's own state and actions? Those are continuous values, not discrete words. How do they handle that?
They discretize them. They basically create 256 bins for all the possible values based on what they see in the training data.
So you're translating the smooth, continuous language of robotics into the discrete, token-based language that a transformer understands.
You got it. And that brings us to the core of the training, this dual objective setup. The model's role, what it's trying to predict, changes based on how you structure the input sequence.
Okay, so when it's acting as the VLA, you give it the text command, the robot's current state, and the images. And its job is to
predict the next action tokens. The prompt is something like, what should the robot do to, pick up the block?
But then you flip it for the world model training.
Exactly. Now, the input is the text, the images, and the action that was taken. And the model's job is to predict the next image.
Ah, so you're telling it, here's the world, here's what we did, now you show me what happens.
Yep. And that forces those shared parameters to learn cause and effect. It has to learn the physics of the world to succeed at that task, which is just a much more efficient way to get that simulation capability.
Okay, so that brings us to the first really big technical problem they had to solve, which is something that trips up a lot of robot learning.
Yeah.
Action chunking.
Right. You want the robot to plan a few steps ahead. But if you just generate them one after another, auto-regressively, the errors build up fast.
It's like a game of telephone.
It's exactly like that. The model is great at language, but it's not as robust in this new action domain. So if it gets action 1 slightly wrong, its prediction for action 2 is based on that mistake, and it just cascades into total failure.
And their first big innovation, this action attention masking, is designed to stop that cascade.
It is. A normal attention mask is causal, meaning action 2 can see action 1, action 3 can see 1 and 2, and so forth.
It builds on what came before.
Right, but their custom mask breaks that chain within the action chunk. It forces every single action step to look only at the original visual input and the text command.
So action 2 isn't allowed to look at their flawed prediction for action 1. It has to go back to the source, back to the camera image.
Exactly. You're forcing every step to be independently grounded in reality. And the charts in the paper show this so clearly. With the custom mask, performance stays high even with long action chunks. With the naive mask, it just falls off a cliff.
So they solved the chunking error, simulations look amazing, but then of course they move to the real world, and the discrete design fails. That classic sim-to-real gap.
It's the story of robotics, and there were 2 real issues here. First, big models like this can overfit very easily on the small, clean datasets you get from real robots. They just memorize the exact movements.
And the second problem was physical. The robot's movement was jerky.
Super jerky. Generating these isolated action chunks, even if they're individually correct, doesn't create a smooth trajectory. You get these stop-and-go movements that are useless for delicate tasks.
Which leads to innovation number 2, the continuous action transformer head. This is what makes it a hybrid model.
Right. So they keep the discrete token set up for the high-level understanding and the world model part, but they add this smaller separate head that's job is just to output a smooth, continuous action sequence.
Why does making it smaller and continuous solve those 2 problems, the overfitting and the jerkiness?
The smaller size just makes it less prone to overfitting on the limited real-world data. And the continuity comes from its design. It uses parallel decoding.
Meaning it generates the entire sequence of movements all at once, not one after the other.
Exactly, and that's the key to the speed. The discrete model is slow, sequential, maybe 3 hertz. This continuous head can run at nearly 50 hertz.
Which in the real world is the difference between a clumsy robot and one that can react in real time.
It's a night and day difference. So you get this beautiful hybrid system. The big LLM brain does the deep thinking and prediction, but this small, specialized head handles the fast, smooth execution.
And the final loss function just combines all 3. The discrete action loss, the image generation loss, and the continuous action loss. It's a really complete package.
It is. Every part has a very specific job to do.
So let's get to the numbers. On the LIBERO simulation benchmark, this thing is a beast, even with no pre-training.
Yeah, 97.4% average success for the continuous version. That's on par with, or even better than, huge pre-trained models like OpenVLA. It just shows how data efficient this unified architecture is.
And it was strong across the board. 99% on spatial tasks, nearly 100% on object manipulation. It's a very general, robust policy.
But the real test is always the real world, so they put it on the LiRobot platform with some tough pick-and-place tasks.
And not simple ones. They specifically use scenarios with multiple targets and lots of distracting objects.
Which is the gold standard, right? Anyone can pick up a block on an empty table. The real challenge is picking up the right block when there are 5 other things around it.
And that's where it really stood out.
Yeah.
It was consistently better than really strong baselines like GR00T, especially in that clutter.
For instance, on one task with distractors, it hit an 80% success rate. That's often 10, 20, even 30 percentage points higher than the other models. An 80% success rate in real-world clutter that's verging on deployable.
Okay, let's dive into the ablations because this is where they prove the synergy. How much does the world model actually help the VLA?
In simulation, it gives a nice little boost of about 5 percentage points. But in the real world, it's everything.
What do you mean?
Without the world model training objective, the success rate on the real robot dropped to below 30%.
So it's a 50 percentage point jump in performance just from making the model also predict the future.
Yes. It's not optional. And the paper explains why. The world model objective forces the network to pay closer attention to the object it's manipulating. So if a grasp fails, it has an internal model to understand that something went wrong, and it can actually try again.
Instead of just blindly moving on to the next step and failing the whole task, it gets a feedback loop.
A physical feedback loop. And it works the other way, too. The VLA helps the world model. Its predictions get better. When they compared the video predictions from their unified model to a baseline world model, the unified one was as good or better on all the standard metrics, FVD, PSNR, SM.
So the videos it generated of the future were sharper and more realistic.
Sharper, more realistic, and more consistent. There's a great figure in the paper showing this. Their model predicts a successful grasp from both the main camera and the wrist camera. The baseline WM, however, sometimes predicts a failure, and its predictions from the two cameras don't even match up.
So the VLA's knowledge of what a successful policy looks like forces the world model to generate futures that are physically plausible and consistent with that success.
Exactly. We should also just quickly touch on two other key findings. First, the discrete tokens, even though they aren't used for the final action, help the continuous head train much, much faster.
They act as a scaffold.
A perfect way to put it. And second, they proved just how essential certain inputs are. If you take away the wrist camera or the robot's own proprioceptive state,
It's knowledge of its own joint positions.
right, if you take those away, the system completely fails in the real world. The wrist camera is crucial for that final moment of grasping, and the proprioceptive state is vital for timing the gripper closure perfectly.
So this all really validates their whole approach. The VLA for the policy, the world model for the physics, and this clever hybrid architecture to make it fast and smooth enough for reality.
The takeaway is clear. Unification is the way to go. It solves the core limitations of both models when they're separate and gives you this incredibly robust, high-performance system.
But the really provocative thought to leave you with is this. RynnVLA-002 got these state-of-the-art results without massive web-scale pre-training.
Which really challenges this dominant idea in AI right now that you just have to scale up the data to get better performance.
It suggests that the right architecture, this kind of unified dual-objective training, can be just as powerful as, or maybe even more efficient than, simply throwing more data at the problem.
So that raises a fascinating question. If this architecture is so effective on its own, what could we unlock if we applied this exact unification strategy, the masking, the hybrid head, the joint objective, to one of those massive pre-trained vision language models that already has all that web scale knowledge?
That fusion could be the next major leap forward for robot foundation models.